Okay, so now we look at a binary search approach to determine that minimum threshold no score that will make the graph to satisfy the strong triadic closure property. Okay, um, so let me give you an idea of what you're talking about satisfying a triadic closure property. So let us say, okay, so these are the no scores of the edges in this graph. Okay, and let us say the threshold no score is zero point 0.0. That means how we classify the edges as weak ties and strong ties. So anything less than or equal to zero point 0.0 will be called a weak tie. So only this edge 1, 2 will be called a weak tie and the rest of the edges will be called strong ties. So now we want to verify or check whether every vertex satisfies the strong triadic closure property. So write down all the node IDs and their strong tie neighbors and weak tie neighbors. So for example for node 1 its strong tie neighbors are 3, 5, 6, 9 and weak tie neighbor is 2. Node 2 its strong tie neighbors are 4, 7 and weak tie neighbor is 1. Node 3 strong tie neighbors are 1, 5 um, for node 3, 1, 5 and 6 and so on. So now what we'll do is go through each node, its strong tie neighbors and check if there's an edge between any two strong tie neighbors. So for example for node 1 we have 3, 5, 6, 9 as strong tie neighbors. So that means we need to check for any pair like 3, 5, 3, 6 or 3, 9, 5, 6, 5, 9, 6, 9. For each such pair there should be an edge between them. 3, 5, yes, there's an edge between them. 3, 6, yes. 3, 9, no, there's no edge between 3 and 9. So the moment we come across a pair of strong tie neighbors that don't have an edge between them, we can say that the strong triadic closure property is violated. Okay, and once one pair is identified like that, we can actually rule out and say the whole graph is violating the strong triadic closure property. But just for completion, I've gone ahead and listed all the pairs that violate the property. So again, 6, 9 doesn't have an edge between them. So again, because of the pair 6, 9 not having an edge between them, node 1 is violating a strong triadic closure property. Now in this case for node 2, 4 and 7, they have an edge between them, so it's satisfying. For node 3, 1, 5, 6, 1, 5, 1, 6, 1, 5, 1, 6, 5, 6, yes, so satisfying. For 2, 7, 8, 2, 7 is fine. 2, 8 doesn't have an edge between them, so it's violating. 1, 3, 6, 9, again 3, 9, 6, 9 don't have an edge and so on. So once for one pair the property is violated, we can stop and say overall the graph is violating the property for that threshold node score, which is in this case 0 0.0. So this is the idea behind satisfying a strong triadic closure property. Actually, let me stop this video here so that this is a separate video. Well, let me show the satisfying case. Well, the satisfying case would be, a better option would be this. Okay, let us say for this graph the threshold no score is 0.33, and based on that, so anything less than or equal to 0.33 will be called a weak tie. Anything greater than 0.33 will be called a strong tie. So these are the strong ties and weak ties. So write down the strong tie neighbors and weak tie neighbors. So now we'll focus only on the strong tie neighbors. Now in the case of node 1, it has only one strong tie neighbor. So if a node has either one strong tie neighbor or no strong tie neighbors, we cannot say it's violating the strong triadic closure property, because strong tie neighbor is kind of considered to be connected to itself. So we could pretty much say to satisfy the strong triadic closure property. And if a node has no strong tie neighbors, we can kind of implicitly say again the node is satisfying the strong triadic closure property. So that's why I say it's not applicable, in the sense that it's only implicit, not like explicitly telling it is satisfying, because there are no two or more strong tie neighbors. In the case of node 3, 1, 5, 6, yes, so 1, 5 have an edge between them, 1, 6 have an edge between them, 5, 6 have an edge between them. Yes, so it is satisfying. Similarly, for node 4, 7 and 8, yes, they have an edge between them and so on. So if for all the nodes it is either S or not applicable, so not applicable is okay, then we can say overall the graph is satisfying the strong triadic closure property for that particular threshold node score. Now you may think then if the threshold node score is 1, according to our definition, then all the edge node scores will be less than or equal to 1 and they'll all be called weak ties. So that means no node will have any strong tie neighbor. So it is like implicitly satisfying the strong triadic closure property. So we'll just say not applicable for all the nodes, and then we say the node satisfies the graph satisfies the strong triadic closure property. So what we basically see is if the threshold node score is 0, a graph is definitely or almost definitely going to not satisfy strong triadic closure property. There is probably you have to dig around and find out, can there be a graph with a threshold node score of 0 and still satisfy the strong triadic closure property? I haven't found such a graph. So for our algorithm purposes, we will assume that a graph is never going to satisfy the strong triadic closure property with the threshold node score of 0. On the other hand, a graph is always going to satisfy the strong triadic closure property in the threshold node score of 1. And this will form the basis of the binary search algorithm, which we will see in a separate video.